So, this is our talk. It is from 0 to 90, achieving peak performance in multi-platform VR development. My name is Devin Reimer. I'm the CE Owl at Owlchemy Labs.
And I'm Andrew Eiche. I am CT Owl and Cable Wrangler at Owlchemy Labs. So Owlchemy Labs, for those of you who don't know us, we are a VR company. We worked on a number of multi-platform VR titles, including Job Simulator, the 2050 Archives, Rick and Morty Virtual Reality, and we are currently working on the upcoming Vacation Simulator.
So building high-quality VR content is hard. Building high-quality VR content that's multi-platform and performant is very hard. So before we get into things, I want to make a note here. At Owlchemy, we are very focused on VR platforms that support positional, tracked, head, and hands. So those are the platforms we're going to focus on in this talk. So let's kick off with the good news. The good news is when it comes to optimization, most existing optimization techniques also apply to VR. And there's a lot of information available online. The bad news is that optimizing is much, much, much more challenging for VR than any other platform.
So let's talk about frame rate, since that is an important part of optimization and performance. In gaming, frame rate has never been this important for comfort and for, in VR specifically. So we must make frame rate, and we have to make higher frame rates than we have before, and we have to do it doing rendering specifically for VR, so it's incredibly challenging. So what frame rate do you run if you're creating a VR experience? So it depends on the platform. So on Vive can run at 90 frames per second. Oculus recommends 90 or 45 frames per second. Windows MR is 90 and 60. PlayStation VR 120, 90, and 60. And the upcoming Oculus Quest is at 72 frames per second. And what does that mean? Well, different frame rates there's a number of different considerations and factors that go into why one would use a specific frame rate. So we can do a little bit of background to help explain.
So let's start by talking about reprojection, sometimes also referred to as asynchronous time warp. This method of warping ends up re-rendering your view rotationally warped in case of a missing frame. But it only supports rotation of the user's head and also will contain incorrect visual information because this frame was not actually rendered, it was generated synthetically. Another one you may hear about is asynchronous space warp or motion smoothing that was just announced. Akin to the previously explained reprojection, it also tries to take into account the head position of the player. But as I mentioned, same thing as reprojection, there will be incorrect visual information displayed because the frame was generated synthetically. Another thing to just think about here is native display frame rate. So this is the actual frame rate that the HMD displays. So how often a new frame is displayed on the panel.
So let's break that down on kind of a per platform level to explain some of this to you. So on the HTC Vive, the native display frame rate is 90 hertz, and we recommend that if you're making a VR experience for this, to target 90 frames per second. It does support reprojection or motion smoothing if frames are missed, but we believe the application should be targeting 90 FPS. On Oculus, the frame rate is the native display is at 90 hertz. Again, we recommend 90 frames per second, and technically, Oculus supports 45 frames per second by using asynchronous space warp. On PlayStation VR, the native display can run at either 120 or 90 hertz. The recommended is 120, 90, or 60. And while 90 and 120 are native, 60 frames per second is reprojected every other frame to reach 120 FPS. And Windows MR, the native displays run at either 90 hertz or 60 hertz, so it's recommended to target 90 frames per second or 60 frames per second. And performance is hard, so why not make your life easier and just use the lowest supported frame rate?
So let's talk back about reprojection. So on PlayStation VR, as Andrew mentioned, it supports 60 FPS. That's reprojected every other frame up to 120, but it uses rotational reprojection. So if you end up having cases where you're seated and you're not moving your head very much, this can actually work quite well. But there's some caveats. Some issues with reprojection are if you move your head, because that's not positionally track those frames, this can happen in cases of standing. Generally, you're moving your head around quite a bit. This will create positional judder for you, which over time can lead to discomfort, and it does for me. Tracked hand controllers are another interesting problem. By nature, tracked hand controllers are relatively close to your head, so the movement of them can appear juddery because every other frame they're actually in an incorrect location. But this also depends on the content. If you have a piece of content where your hands are really low or they're not generally in focus right in front of you, you might not notice it. And then lastly here, physics or certain animations. If there's certain predictable movements of, say for example, something's moving very linearly that's predictable, you will know where it should be visually in the next frame, and then that can appear to be stuttery across your frame. So for people that have played Job Simulator, you might know that we have all of those issues. And so this becomes a challenge to think about. We also mentioned asynchronous space warp that deals with positional head, trying to get that factored into the synthetic creation of a new frame. So asynchronous space warp on Oculus and motion smoothing for Valve support running 45 frames a second. So this, like on PlayStation VR, ends up synthesizing every other frame, but in this case gets up to 90. So this ends up resolving some reprojection issues like head movement. But there's some new things that come up here. Because the frame rate is very low, 45, I know it's comical, it's like 45, super low frame rate, but in VR it's very low. Because that is the actual true render rate, things can appear to stutter even more than on PlayStation that runs at 60 reprojected up to 120. So just be aware of that. Very recently, Asynchronous Space Warp 2.0 and Valve's motion smoothing were just announced, and we haven't had a chance to play around with them yet to know exactly what things have got better.
So this is kind of a developer beware warning, all of this that we've been going over. So you need to understand what your content and its needs. And if you are relying on reprojection methods to make frame rate on PC or console, you're going to have an incredibly difficult time if you have to port that content to a lower spec platform like a standalone VR. So let's talk about Job Simulator's frame rate. On Vive, Oculus, Windows MR, and PlayStation MR, or PlayStation VR, we are at 90 frames per second on all those platforms. On Rick and Morty, on Vive, Oculus, and Windows MR, we are also at 90 frames per second. But we can't say the same for Rick and Morty Virtual Reality, as the PSVR port was done by another studio and actually runs at 60 frames per second reprojected. So now I know what frame rate to hit. How do I do that? Well, there's an old rule about premature optimization, but it's actually very different in VR. Frame rate's incredibly critical to the content, so if you aren't making frame rate and you're attempting to test your content, you're going to be sick from the start and have a very bad time. So the better rule in the case of VR is to not optimize the wrong things. We work on performance from day zero. And it helps set us up for the future, so there's less of a gap between where we need to be and where we currently are when it comes to shipping the game. And it also gets us, we check often.
So there's a lot of factors that go into how performant your game is going to be. One is art style. It's very important that when you're choosing an art style, you also make sure that you're choosing an art style that meets your performance goals. So the more performance overhead your art style has on your game means the more performance you're going to have to do. And then even to kind of extend that is certain art styles might even prevent you from shipping on certain lower spec platforms. So one of those things that impact art style is post-processing. Our thoughts on that is that you should generally try to avoid it if there's two factors. So the first one is if it's fundamental to your gameplay, or it's very important to the look of your game. Like your game will not look the same without it. The reason is that post-processing is very expensive on lower spec platforms. And so you have to think really hard about if you're putting that in, if you had to, in the worst case, rip it out on those platforms, would your game be functional or would your game look like the same game? In our games, we use simplified bloom, but only on platforms that have the performance profile to handle that, as simplified bloom is not fundamental to our game itself.
Game mechanics are another place that you should watch out for. Specifically, like certain game mechanics may be very costly performance-wise. And unlike other parts of your game, you can't just remove your core mechanics. So if it's incredibly difficult to optimize, it might be a really important place for you to beware. So an example of the game mechanic optimization challenge is Rick and Morty virtual reality. We had this portal, and there was a lot of optimization required. It was a very complex camera setup where we had these kind of objects existing in two spaces and things moving between them and physics moving between them. And but due to the intellectual property as well as just kind of what the game was about, it was core to our game. So we went in knowing that we were going to have to optimize this, and that helped. So now let's get into some practical tips. So we avoid update/late update like the plague. It can be useful, but you should be careful. You should try to make it absolutely as minimal as possible. And what we do is we use event-driven code, and that's kind of what we recommend. So try disabling behaviors that do have updates whenever possible if the update is not necessary to run. We also avoid using coroutines. Coroutines have a lot of performance and memory issues. We found that a lot of our bugs come from coroutines. They're very difficult to debug. And we realize they aren't completely avoidable, but again, like the update, late update, try to minimize it as much as possible. One of the tools that we created to help us minimize it is something we call Time Manager. So Time Manager handles invokes after a set period of time. So a lot of our code is something that just waits for a lot of our coroutines we found were basically just waiting for a chunk of time and then executing something. And even more so, executing something statelessly, so it didn't need to carry state over that time. So we could make this singular time manager to handle that case. That got rid of a ton of our coroutines. We could heavily optimize that time manager, and that performance gain was brought across all of those former coroutines.
So Unity UI, our recommendation is just to avoid it. We're slowly stripping it out of all of our existing games and introducing no more Unity UI going forward in our games. It turns out it just has too much overhead for VR. And so the overhead comes in two ways. So the per frame cost, particularly on things like layout, which is like one of the core features of a good UI system is doing some layout. That ends up having a per frame performance cost. And then recaching that it does when things become dirty ends up having huge spikes. And those spikes kind of guarantee a frame drop, sometimes multiple frame drops. In a game where you're running 30 FPS on a flat screen, it's like, okay, I maybe blew through a frame because it ran 40 milliseconds, fine. It's like, but in VR, that's like 4 frames that you have lost, and you shouldn't be working towards never losing a frame. So you might be thinking, okay, how do we do it then? How do we handle UI? Not well. We use sprites. And we've been working on a new UI system that from a performance standpoint is faster, but from a using standpoint is not faster. So right now it's kind of painful to work with. I wish I had a good answer for people here of what to do. It's just very problematic, particularly when you're trying to target lower spec platforms when it comes to performance. So render textures and multiple cameras. These are very, very challenging on lower spec platforms. Sometimes they are very useful, but you don't have to think about them as like an always-on cost. Sometimes you can use them on demand. So for example, the job board in Job Simulator, it has a UI, and what it does is it shoots a camera at that and does a render texture for that. But we end up checking when that job board is dirty. It does animate and things move around on it, but that's actually pretty infrequently. So by turning that camera off, we end up having that job board only being one draw call, which actually helps with performance. In Job Simulator, we also did the bot faces, and so the bot faces with a camera that was a render texture, and then we did a lot of things like turning that on and off when the bot's faces were animating. But in that particular case, that ended up being too costly from a performance standpoint, and why we did ship Job Simulator with that on PlayStation VR. For Vacation Simulator, we actually went through and replaced it with a complex shader, so we didn't have to use a camera at all, because it turns out just simply the act of, even if you're doing just a few simple things with a camera, the simple act of rendering that camera is pretty heavy. And then lastly here, in Job Simulator in the convenience store, we had this little game where you could drive this bot around on the floor to clean the floor, and it had a first-person perspective view that was replicated on a display in front of you, and you can kind of pilot it around. But on PlayStation VR, that ended up being too costly from a performance standpoint. And so when we went through that, one of our developers actually converted it into a mini-map that was a top-down thing that looked like Pac-Man you were driving around, so no additional camera render. And the interesting thing there is a lot of people, myself included, think that it's actually much more interesting and cool in that method. So why I'm talking about a lot of things that seem like, like maybe doom and gloom, it's like some of these constraints can actually lead to better games. When you're actually using multiple cameras, particularly something that you're doing a lot of time, like it's not just I'm shooting it and then turning it off, you have to think about multiple cameras and how they impact VSync. So I mentioned that you should generally avoid using multiple cameras, and then here we are in Vacation Simulator. We built a camera that you hold that you can see another view all the time, and it's fundamental to the game. And so that's a challenge for us. What we've discovered is that you should generally avoid calling camera.render manually in VR. And so the reason for this is that every platform either uses VSync or something like VSync to lock your rendering so the next frame is always presented at the same time. But this means, as a side effect, is if you call camera.render during that period of the VSync or the VSync-like, it will just do nothing. It'll lock your main thread, and you won't actually get any additional work done. So we ended up discovering that from a performance standpoint, it actually is better to instead toggle the component for that camera on and off as you need it. And then that way what will happen is the platform will set up, get ready for camera renders, and then do yours at the right time without blocking your main thread.
Shadows, they require a lot of overhead, but they're a huge win for visual fidelity. So bake them if you can. If you're using mixed shadows, you could have more overhead. We actually found in Vacation Simulator that when we did a bunch of tests with mixed shadows, it was less performant than having real-time shadows. Rendering shadows requires a depth buffer, which is also a lot of overhead, so it's something to take note of. And on Job Simulator, we currently use the highest quality shadows, which is very hard to deal with from a performance standpoint, but we think it adds to the visual fidelity. Physics is also difficult, and again, just setting ourselves up, we rely on physics as a core mechanic of our game, so we go in knowing this and optimize for it. And we allocate a lot of perf to it. It can widely fluctuate, so you need a lot of clearance. You're going to be optimizing for the worst case physics frames, and then seeing that your light frames will have a ton of time to spare, and that's okay. And another point of note is in Unity, multiple physics frames can and will run on the same frame, which means it's going to double your time. And it also means that fixed update can and will run twice. And we do have to put some code in our games to detect when that happens, when fixed update runs twice in a frame.
Yeah, sometimes we just do things slightly different in there because of the performance overhead we know is going to incur in that frame.
Your goal should be to keep most rigid bodies asleep almost all the time. And to help us do that, we built a tool that goes through and finds all the rigid bodies every frame and prints it out on the headset when those rigid bodies are awake. And that tool looks kind of like this. It helps us catch a ton of issues. So we've caught stuck physics hinges, which is like a door that's like wiggling. We've caught animations that have rigid body, that cause the rigid body to wake up because it's moving a collider, especially deep within hierarchies where it might not be plainly obvious. And then we've caught always falling rigid bodies, so spots in your geometry where you may not have had a collider and then the object just continues to fall. It's great for finding those things.
Yeah, I should point out is like this is relatively trivial to write. It will kill your performance running through all those things every frame, but that's not what you care about during this test. You care about what's active. So it's very important to think about where you are currently bound, on the CPU or the GPU. Generally, we find on PC we're GPU bound, but on something like PSVR, we're CPU bound. It's very important that you determine where you are bound to optimize for that. There's a lot of things online of like looking to try to determine the best way of where you're CPU or GPU bound, but make sure you're optimizing the right stuff. If you end up being GPU bound and you're spending a lot of time optimizing the CPU, you won't do yourself any good. So just kind of a quick case study to show how the final shipped version of Job Simulator performs after it's been optimized. So here's the CPU performance of Job Simulator on PlayStation VR. So as I mentioned, we're generally CPU bound on PlayStation VR, so this is what we cared about the most. So about 3.5 milliseconds ends up going to rendering, millisecond and a half goes to shadows, 4 milliseconds goes to physics, about 1 millisecond or less is all of our code in the game, and then we have a little less, around a millisecond of clearance on every frame to end up dealing with those performance bubbles that end up coming in to play. And so it's definitely a challenge because it means, for the most part, every piece of code that we write in the game needs to operate in less than a millisecond combined, which is a pretty big challenge, but it means that we have to think about all the time what we're doing, and we care very much about what happens every frame. So when it comes to rendering, the VR resolutions are very high, so it ends up mattering more than on traditional game development. So just some quick things just to pay attention to is just avoid overdraw, be very careful of transparencies, and make sure you atlas and you're doing a good job of atlasing the right things. Simplify your shaders and reduce draw calls. On almost every platform, you're going to be draw call bound. So draw calls are your biggest enemy, and you need to think really hard about what is rendering. When it comes to shaders, we try to use a small number of simple shaders, but sometimes we use complex shaders. Like I mentioned, the bot faces in Vacation Simulator use a very complex shader, but it ends up saving us by doing that. It also helps when you do optimization, because if you end up having a small number of shaders, you can focus on optimizing them, and it'll be big wins across the entire game. If you end up having a ton of shaders, it's going to be a lot more work to optimize things. And then generally, our shaders just support one real-time directional light.
And as a point of note, we build our games and art style to support that one directional light.
Yep.
So another technique we use is multiple frames. So we'll split tasks across long-running tasks across multiple frames, and that happens very often. Sometimes we also only do things every few frames, and then we can take the tasks that are all running every few frames and offset them separate from each other. Generally, we use 3 frames as a standard, so 90 divided by 3 is 30 FPS. So if you're okay with something running at 30 FPS, like this secondary camera on this mirror, then you can just have it execute there, and that'll get you some performance wins. We don't make garbage, and you shouldn't either. Don't make any garbage. When the garbage collector kicks in, you will miss a frame. So your job is to make sure it kicks in very, very infrequently. We strive to create no garbage in our code, and kind of as a point of how we figure that out, the Unity profiler is very good for quickly tracking garbage creation and collection issues. And then we profile often, speaking of the profiler. The Unity profiler is excellent. They've done a great job creating a very competent profiler. And then each platform has its own tools, and you should use them. There's tons of resources out there on how to use the profiler and how to use these tools, so you can find those.
Just because I think it's interesting, here's a profile of Vacation Simulator on the beach, but this is work in progress. Also, this is running on my pretty beefy PC at work. And so you can see here that we are running less than 11 millisecond frames, but the interesting thing here is that whenever you boot up the profiler and you're doing that and you're running an editor, you end up having a cost here. And so the cost here between the profiler and the editor overhead is about 4.5 milliseconds. So really we're running about 6 millisecond frames. And so this is still work in progress. We still have work to do. But just make sure, like if you have a relatively beefy PC and you're targeting lower spec platforms, it should be running ultra fast. One of the other things that ends up being helpful here is that if you end up running fast enough that you can have the profiler open without missing frames, it won't actually muddy your data as much. So on that note, when it comes to profiler tips, don't use the deep profiler, at least until you've discovered what the exact function you want to dig deeper into is. So as I mentioned, it'll muddy your data. Even the simple fact of if you're barely making frame rate and you have the profiler open that causes you not to make frame rate, what will end up happening is your frames will end up being structured in different ways because fixed update has to run all the time. And so if you end up missing lots of frames, you'll end up having fixed updates pile up, which can cause cascading things in your performance profile. And so it'll actually muddy the data. And the deep profiler is even more expensive. And it'll end up having a lot more cost throughout all the different traces in there. So just be very careful. You don't want to use the deep profiler to figure out how long something is taking. You want to use the deep profiler to figure out what the deep level problem is. I also highly recommend using the timeline option in the Unity profiler. VR frames, because frame rate is so important, are structured in a very specific way. And so sometimes what will end up happening is you're like, okay, I'm CPU bound, let's optimize CPU stuff. But really you're optimizing something in the CPU where it's not the bottleneck at all. And if you open up the timeline, you'll actually see what things are the actual bottleneck. Another unfortunate thing is if you use graphics jobs like we do, the GPU profiler will not work. You have to turn graphics jobs off to get the GPU profiler to work. But by definition, when you turn that off, you're changing your GPU profiler, what the GPU profiler would see, so the data ends up being muddy. So that's just an unfortunate thing, but just something to be aware of because it's not initially obvious why that is going wrong. Also beware of heavy coroutines. They will show up in different places in the profiler, and sometimes it's easy to overlook them. Because generally you're looking through the profiler and you're like, oh, okay, I'm looking at my update, which is a whole bunch of things, late update, it's a bunch of things. And then you don't notice that further down there is something that's taking like, 0.2 milliseconds, which doesn't look like a lot because you assume it's a bunch of things, but it ends up being a single coroutine doing something silly. So just be very aware of everything in that stack. And lastly here, the profiler doesn't make it as visually obvious as I would like. When you end up having what looks like a heavy physics frame, it might be multiple physics frames. Just take a look at how many calls are being called to that you're not accidentally freaking out that something is going wrong in your physics thing. It might be just multiple physics frames at that time, which is totally fine, but it just needs to be accounted for. As I mentioned before, that draw calls are probably going to be your biggest enemy, so the frame debugger is going to be very, very important for you. We very often step through our game frame by frame, making sure that every draw call makes sense and that it's actually what we want, because there's a lot of things that can happen to cause that to not be what you want, and you'll make sure, and this will also help you to figure out kind of what should be combined and what should be removed.
So 3D audio. It's very, very important in VR and very important to your player's experience, so do it. That's great. But it does have a performance overhead, and that performance overhead is dependent on what spatializer you're using, so it's just something to be aware of. The good news is, if you're developing for PlayStation VR, they have a built-in hardware spatializer, which means that it comes at almost no performance cost. As far as audio management specifically, we built a pooled audio manager that handles most our audio playback. And so we have these like incredibly dynamic worlds with a lot of audio sources, so we wanted to be able to control the number of active audio effects playing at any one time. It also gives us per platform control over audio sources, so it has a nice added side benefit of that. And without talking about what performance talk would be complete without talking about pools. So we use pooled particle effects. It helps our base performance, but it also helps us cap the max number of effects that we play at any time, and that has an added game design side effect too. And it also allows us to swap out the different qualities of effects. So on different platforms, we just put a different effect in the pool, and that changes the quality of it. For instance, a good example of this is burning 20 things on the grill. So 20 smoke effects would be bad for performance and potentially confusing. So we use the distance from the player's head to determine what is important and put those and play those particle effects.
So in Vacation Simulator, we ended up building our own LOD system. And some of the reason for this is our game, Vacation Simulator, has zone-based teleportation. So you pop between these predefined zones. And so we needed control for that. We didn't care as much about I'm just like natively traversing the environment. And so we could do a lot more clever things here. And it gave us more control from a performance standpoint. And also helped us deal with a lot of fun edge cases. So here's an example of glasses. We have a lot of glasses in the game that bots can wear, that you can wear. The general default state is they end up having an opaque and a transparency call. But for the LOD, we made a new version that is just a single opaque. This works really good when objects are far away from you, but there's things that pop up with this. So for example, let's say a bot was wearing those and the bot moved far enough away that the LOD would kick in. It looks really weird when you can see the eyes of a bot through the glasses and then all of a sudden you can't. So we end up having custom logic in there that determines, oh, it's being worn by a bot, therefore do not use the LOD system for that at that time. Batching, static batching, use it, but be very careful not to move things that are static. For us, it presents an additional challenge because depending on how much real space that you have in your real world, we dynamically resize and go through different layouts in VR. But that means that we end up moving things around, and so by marking things as static, we can't move them. So this presents a pretty big challenge for us. So because of that and because of lots of other reasons, sometimes it ends up making more sense for you to combine the meshes yourself because you end up having more control over how things are actually working. Dynamic batching. The question is, should you use it? Well, it depends. I think most people don't understand how it exactly works, and it's incredibly limiting. I'm confident I don't know exactly how it works, because sometimes things surprise me. For example, you should have no more than 300 verts, or no more than 900 vertex attributes, but even that has exceptions. It has to be the exact same material, and not an instance of the material that also is identical. It has to be the exact same material. And then there's just lots of other edge cases that come up with this. On top of this, it has a CPU cost. So you have to make sure it's actually helping you, because on platforms where you're CPU bound, it might actually be detrimental. But between doing profiles to make sure that it is helping you and taking a look at how the frame debugger is actually handling things, you can kind of determine if this is right for your piece of content. GPU instancing in shaders. We've frequently started using this. We haven't, as of yet, found much of a drawback. So I recommend writing it into your shaders to support this. And then, once again, use the frame debugger to make sure that things are working as you intended. It's very easy to just like write something and assume it's doing what you expect, but the frame debugger will tell you for sure.
So Unity jobs are very cool, and we're really excited about them. We did start to do some work converting some of our existing systems to use the Unity jobs, but for our current projects, we haven't found any big wins yet. It turns out the setup of the system has been a lot heavier than the actual work that the system is performing. So we still have some plans to try to use it again, but haven't found success in an actual shippable use case, and we'd love to talk to folks that have.
Yeah, it's a little bit of a chicken and the egg here, where we don't have tens of thousands of things to do because we wouldn't have been made performance if we had had that. But now that we have access to that, we can kind of start thinking about problems in different ways going forward.
Game object hierarchies are, this is a potential place where you can lose a lot of performance. So if you have objects that move, drastically reducing their hierarchies is a huge performance win. A good part of our optimization phase is spent finding and simplifying hierarchies in game objects. And then a little bit of production advice, managing your Unity project. We don't branch our platforms in source control, so everything in our platforms is in the same project, and that means we have to build a bunch of custom tools and a bunch of custom things to kind of swap between the platforms, and that's a huge headache to do those things, but it has big optimization wins by all living on the same single branch. So when you do optimization work on one part of the game, all the platforms win. So this meant when we had done the work to optimize for PSVR on a job simulator, we got to bring those wins back to PCVR. Now, just one point of note, be careful, because sometimes the optimizations you're doing on one platform might be faster on that platform, but slower on another. And again, that's a lot of that CPU, GPU bound or dependent on the platform.
Yeah, we have to do a lot of QA, because essentially what ends up happening is like, oh, we want to make an update to make this platform faster. And it's like, did we wreck something on another platform? But it's totally worth it.
Yeah.
So thinking about the future, a very unique thing is unique to VR here. In traditional hardware, generally what happens is over time, the horsepower increases. So if you build something for the latest now, over time that's going to get faster and faster and your things will run better and better. But in VR right now, we're not seeing this happen. Actually, we're kind of seeing the opposite happen. So the birth of modern VR happened on the PC, and PCs are very fast. And then PlayStation VR came out, which is not as fast, and now we're on the kind of the horizon of standalones, which are not fast. So I think the important thing to point out here is that if you're working on content today, it's hard to recommend targeting the highest end available platform, because you're going to have a very tough time going down to lower spec platforms. So just be very, very cognizant of this. This is not going to happen forever. It's not going to be a continuing thing down, but at least for right now, this is what we're seeing. So one thing I just want to make very clear to everybody is that we think multi-platform is great. It is great for the industry. It is great for your business. It is great for game development. It's great for players. So we highly, highly recommend doing it. It is a challenge, but it is very rewarding.
And if there's one big takeaway from this talk, it's that VR optimization is incredibly project specific. So you hear us talk about a lot of techniques that benefited us, but every project is different. So you're going to have to look into your own project and see where the challenges are. You know, we talked about the design challenges or you know, kind of different techniques and technologies that you can use. So that's a place for you to explore. And kind of a closing thought here, performance is not polish, so do not leave it to the end. All right,
Questions?
We'll take questions.
So yeah, we got some time. Come up to the
There's mics in the back, yeah.
Yeah.
In my particular VR game, there's a lot of physics and flex being used, and it really is dragging performance down. 90 frames per second is not realistic. Would you say that a good strategy for games like mine would be to have the update calls rendering at 90 frames a second, but having the scene update, let's say at 24 frames a second in fixed update?
So, so you're saying running a fixed update slower than your general?
Yes.
Yeah.
Yes.
I guess that really depends on how much you're actually interacting with the world. If you have lots of objects that are moving physically, right, and you have the fixed, like say you're running at like 30 FPS on the fixed, like they will just like do, everything will be stuttering. If you end up interacting with it directly, it gets even worse. And that's why we at least for all the stuff that we make, because there's a lot of physics object interacting with them, it's very important to have the fixed time step line up exactly with your update.
And to let you know, we do a lot of physics, and we don't put upper limits on the player. Players can make hundreds of objects and just swat their hands through them and have them all collide.
Yeah, and so we do a lot of optimization. So I'm not sure exactly what your piece of content is like, but I would getting to 90 is very important, and it's just to go through and think about how the physics stuff is currently interacting and what it is doing, and does all that need to happen in physics? Is there things that you can do to optimize that? Is there things you can do where we have lots of objects, like a lot of objects you can interact with, but in a general frame, our physics is pretty tiny because essentially what happens is almost everything is asleep and not moving at all, and it's only certain things and certain times that are kicking in. So that's like an area to look at.
Is your focus on 90 frames a second so important that you're basically willing to cut away content and gameplay to make it happen?
Yeah, very, very much so. It's so important to us that we don't make our users uncomfortable. Not only for our future users, but for the future of VR in general. Is like, we do not want people to go into an experience and have discomfort, because then that means it's going to be so much harder to convince them to go in again.
Are there situations where you...
I think we're going to move on to the next question. Thank you.
Thanks.
Thank you. This is really amazing. How many draw calls would you see in Job Simulator?
It's a good question. I think somewhere between 400 and 600 on PlayStation VR is where we ended up landing.
Yep. Two quick questions. You said you're talking about Unity UI being very non-performant. Is TextMesh Pro a better option?
We love TextMesh Pro. We use it everywhere. It's all over. To the point where on like a design thing, sometimes we mess up the TextMesh Pro as a test tool to make sure that you don't have to rely on reading something to understand. But yeah, no, TextMesh Pro is great. It's a fantastic tool, and we'd be sunk without it. So, yeah.
Yeah. And like on that note, if you end up having a lot of text and it's dynamic and stuff like that, one thing that you can do to kind of help with the number of draw calls is you can, like, say for example you have a board and then you've got a whole bunch of different dynamic text on it, but it's not updating very frequently. You can shoot a camera at it, create a render texture, and then it's like one draw call, and it saves you the entire perf for the entire thing. But that's just like one avenue that you can take.
My other question is, you said that don't use updates, don't use coroutines, use events instead. What about just the technique of using like one update to rule them all that calls out to everything else?
It's kind of what Time Manager is. That's a lot of what that kind of is like consolidating them.
Yeah, there's definitely drawbacks to it. So having one update, you can actually get quite a bit more performance of like calling the right things. It means it makes it a lot simpler to be like, oh, I'm going to subdivide that across multiple frames or call it every third frame or stuff like that. But it actually makes some of your profiling harder. As I mentioned, not to use Deep Profiler because essentially it wrecks your performance so bad. When you end up doing that, when you look at the profiler, it's like everything will be coming out of a single function call, and you might not be able to drill down far enough. So it's not without its challenges. That might be something that you do a little bit later stage in your development, because it's not that hard to to implement, but yeah, it's something
And I
to
think on the point of avoiding it, there are many times where it's unavoidable, but it's a lot of times what we're encouraging our developers to do is to try your hardest not to use it, and then if you have to, use it.
Thanks.
Thanks. Any other questions?
Hi, so you mentioned TextMesh Pro. You also said that you don't use Unity UE because of performance. So how do you use TextMesh Pro? Is it just like the flat thing under a canvas, or have you got some other way of doing it?
So there's two variants of TextMesh Pro, and it's not obvious in the editor, unfortunately. So one uses the canvas and actually does it through the Unity UI, and one doesn't. And to use the one that doesn't, because essentially you won't have the cost of the UI aspect of it.
Okay, so you completely avoid Unity UE, even the canvases. Yeah.
Yep.
Okay, cool. Thanks.
I just want to know what's your approach on anti-aliasing in your VR games?
Yep.
Yeah.
So anti-aliasing, in Job Simulator we did 8x. Anti-aliasing is very important. But that said, we've done a lot of tests to kind of determine, for example, on PlayStation, where good anti-aliasing lands. We can't really tell the difference between 4 and 8. And so I think going forward, we'll probably target 4 because it does bias some perf. The reason we did it on Job Simulator was we ended up being CPU bound, so we actually had some room to spare there, but 4x. And I think that you shouldn't go below 4x
Right, you should definitely anti-alias.
And
That's
definitely
the first. That's the first.
4 is
thing,
about
yeah.
as low as you should go.
So is it MSA you're talking about?
Render scale is different. And so we generally on platforms by default target about 1.4 times the native resolution of the headset. That's what we do on everything as of right now.
So, streaming is so absolutely important, and one of the difficulties that we face in VR is that people can't see what you're doing in there. Do you have any recommendations for optimizations for a game which is designed around mixed reality filming of the game?
From a performance standpoint?
Yeah.
The kind of the things I was talking about of when to render that camera becomes very important. And so I think toggling that camera for mixed reality on and off is beneficial. Running it at a reduced frame rate is beneficial. But there's just a lot of performance overhead with that. Generally, when it comes to mixed reality stuff, you have a very beefy PC, so you can just throw more hardware at the problem. And so at least
typically you're even running like OBS on top of it, so you have that performance chunk. So yeah, there's a lot that we can do, and then there's a point at which it becomes kind of a hardware problem.
Cool, thank you.
Any other questions?
I think that's
All right, thank you.
Yeah, thank you.